présentation en français, mais je pense que Mathieu fera sa présentation en anglais, j'imagine. On a le plaisir d'accueillir Mathieu Sellier. Alors, Mathieu, je le connais depuis assez longtemps parce qu'il est franco-néo-zélandais, comme moi d'ailleurs. Mathieu est prof à l'université de Canterbury, c'est à Christchurch, sur l'île du sud de Nouvelle-Zélande. Et il a travaillé sur beaucoup de choses. Ça fait de nombreuses années, donc il est en Nouvelle-Zélande. Ça fait combien de temps? Ça fait
Presque 20 ans.
presque 20 ans.
Ouais.
Voilà, et donc Mathieu va nous parler de propriétés rhéologiques mesurées à partir des mesures de surface libre. Un peu
Voilà.
Mathieu.
Merci. Good morning, everybody. So I'll do it in English. And actually, for me, I've lived in New Zealand for a long time. It's probably almost easier for me to do it in English. So first of all, thank you for the opportunity to come and present this work today. And I thought I'd start by doing in New Zealand, there's a concept which is called mihi mihi. It's a Maori concept, and people are very big on introducing themselves, saying where they're from and what they do. So I'm going to do my mihi mihi. So I'm from Grenoble originally. That's where I was born and grew up. Did my undergraduate studies there. Then I did my PhD in Leeds in the UK, and this is where I got interested in thin film flows, which is a theme of my research ever since. Then I did a postdoc in Kaiserslautern, so that's in Germany, and there I got interested into hot stuff. This was about glass forming, making lenses with a lot of with high precision. And after that, I went to New Zealand. You see here, so yeah, Christchurch on the South Island, as Stefan just said, and I've been there since 2006. So what do I do there? I'm generally speaking interested in flow that involves interfaces and inverse problem in a sort of broad sense. So I like to do modeling. This is what I do. So basically, I've used a range of methods, including lattice Boltzmann. This is a droplet impacting on a textured surface modeled using lattice Boltzmann. So I've been interested in a wide range of projects, including, let's just see if I can play this video. Okay, this is forensic science, trying to understand bloodstain formation. So this is some simulation we did. So glass forming, I've already talked a little bit about. In New Zealand, we do a lot of, we are a big producer of milk powder. So this the context for this was understanding the impact of milk droplets on surfaces, texture surfaces. Problem involving erosion or digital microfluidics. And so the other area of interest of mine is inverse problem. And I like to use this sort of cartoon to illustrate what I mean by this. Basically, this is just a relationship between cause and effect. And if you, in forensic science, usually what you have is a blood stain, and what the forensic scientist wants to know is what happened when the blood stain was generated. So you usually what we can do reasonably well is understand the direct problem where you've got blood formation and impacting on a surface and generating this beautiful pattern. I guess it's already a complicated problem, really. But doing the reverse and trying to understand, hey, this is the pattern I have, and I want to understand how it was formed is a challenging problem. And in order to solve such problem, you need observations, such as this stain here, and a predictive model, which of course is going to be based on the Navier-Stokes equation. So here we've done a number of things, and I just picked 3 cases. So if, for example, in glacier flow, you can easily measure things at the free surface, but not so well at the bottom. So we've tried to basically reconstruct the bedrock from measurements at the free surface. We've done similar things about river. Stefan, that might ring a bell. That was from students that you examined. And our control of flows. So here we've got control of flow of a cylinder by applying suction just to eliminate the wake. So these are a few examples. But today what I'm going to talk about is trying to understand the rheology of a fluid just by looking at how it flows to some extent. And the fact that the rheology affects the free surface is very obvious on this picture, which is why I like it. I mean, all these fluids, they are all subject to the same gravity force, and yet when you look at the free surface, there are striking differences. So clearly the free surface has got some signature of the rheology. So rheology, of course, is important in many contexts. When you're producing food, pasta, ice cream, in the building sector, if you want to, actually this is the University of Canterbury. There was a concrete pouring. That's the effect of rheology is very important. Our manufacturing of glass is another example, but of course there are countless examples where the rheology of the fluid matters a great deal. So typically, when it comes to rheometry, that is the measurement of the rheology, we use rheometer. That's of course the first stop, because rheometers provide you well-defined flow conditions that allow you to describe the rheology of the fluid in a way that is consistent and reproducible. Okay, and so you've got what's called viscometric condition, where you apply a reasonably well characterized strain rate, effectively, and therefore you can measure, by measuring the torque, you can quantify this rheology. The kind of rheology I'm going to be talking about mostly today, they are sometimes referred to as generalized Newtonian fluids, and so basically this is what we see on that flow, these flow curves here. This is the shear stress on the y-axis, the shear rate on the x-axis, and of course if you've got a straight line, you've got a Newtonian fluid, the slope of which gives you the viscosity, and then you can have dilatant fluids, so shear thickening. So if you look at the slope of this curve, it increases with the shear rate, so the viscosity increases. So that corresponds to a power law exponent here, n greater than 1. You can have shear thinning fluids, and then so these are old fluids which have no yield stress, but some fluids have got a yield stress. So that means you need to apply a certain amount of stress before they start to flow. Okay, and so I'm going to talk a little bit about power law fluids, which are fluids described by this relationship, but without the tau 0. And I'm also going to talk about viscoplastic fluid, where there is a yield stress tau 0. All right, so there are many situations where the flow is such that you cannot use a rheometer to quantify the rheology. I'm going to talk specifically about two examples, which are aerosol particles. The problem here is that the samples you collect, they tend to be too small, so you don't have enough to put in your rheometer. I'm going to talk a little bit about lava. As you can imagine, lava is hot, corrosive. You can't just put it in your rheometer to do measurements. And another example which is actually connected to lava in terms of rheology is landslide. I mean, landslides is collections of particles of different sizes. So if you want to put it in your rheometer, this is not very practical. All right, so again, we'll try to infer the rheology from what we can see at the free surface. So questions we try to answer is: how much information is sufficient information? Can the properties be uniquely recovered? And in order to test this, I'm going to go through a number of examples which are laboratory examples, so arguably well-controlled conditions. So the first one actually was motivated by Alan Bertram from the University of British Columbia. So he's interested in aerosol particles, And again, this comes in very small sample that you can put in a rheometer. So he came up with a technique which he called the bead mobility technique, and which I'm going to describe in a moment. And Alan is a chemist, so he knew a lot about the chemistry, but he wanted to know more about the fluid mechanics of the process. So this is kind of where I came in. So why was he interested in aerosols, and specifically organic aerosols, here OA, because they play a very significant role in atmospheric models, and therefore to predict things like climate change. So those organic aerosols, they've got a viscosity that varies by many orders of magnitude depending on the relative humidity. This is what's shown actually on this graph here. You see the viscosity. This is 10 to the power 0, 10 to the 14, 10 to the 14 here as a function of the relative humidity. So you see that the viscosity increases steeply. You see the size of this. This is the size of the error bar. So that gives you a bit of a feeling for how poorly quantified these things really are. So standard viscometry, again, these are not really are not suitable because the amounts of aerosol material that you can collect in an environmental chamber is too small. So that's on the order of microliters. And if you want to use a rheometer, you probably need at least milliliter. So that's not suitable technique. There are other techniques that have been used to sort of produce these points here, but they tend to rely on either very complicated instrumentation or very expensive ones. And also they tend to have a very limited range of viscosity. So actually I'm just going to skip this one and talk about the bead mobility technique, which again was developed at UBC. I mean, the concept is fairly simple. You put so your aerosol material, you deposit it on a glass slide. So you form like a droplet, if you like, and beads were inserted in that droplet, and so beads which could be visualized from microscopy, and then you subject this flow to you subject this droplet to a cross flow in an environmental chamber, which is what you see here. So those beads, of course, are going to recirculate, and the whole idea of the technique was to relate the velocity of these beads to the viscosity. So here in that case, we assume basically a Newtonian rheology. So we're just trying to estimate the viscosity. This is what experiments look like. This is based on the technique was sort of proposed back in 2013. This is kind of what this is a sequence of pictures of the droplet. So you see typically this is about 20 microns. The flow here is going from right to left, and you see some of for example, this bead here, the green bead. Actually, it's going against the flow that is actually produced in the environmental chamber. So here you see some streamlines. It's important to say that the location of those beads in the depths is not controlled or characterized. So in fact, this explains why those beads are traveling against the gas flow. But basically, the idea is that they looked at this velocity, took some average, and then came up with correlation curves. So this is what the correlation curves looks like. And if you think about it, this is a lot of work. I mean, they've used a whole bunch of different fluids here, and well-characterized fluids. And for all those fluids with a range of viscosities, they've put them in the environmental chamber, exposed them to flow. So producing this calibration curve was a tedious exercise. One of the issues with this calibration curve as well is that it's not very well, if you change the size of your droplet, if you change the conditions, the flow conditions, well, it's not very well clear if this calibration curve still is relevant or valid. So this is when Alan Bertram from UBC asked me, can we do something better in terms of fluid mechanics to sort of understand what's going on. So I'll just say that this calibration curve here, this is what the straight line that you see here. They fitted it with a power law, with a prefactor A, given by this, and an exponent suspiciously very close to -1, but not quite -1. So I'll tell a little bit about the model that we developed. So this is, the idea was to make something simple. So we assumed a plane flow, Newtonian incompressible for the inner, that's inside the droplet, and the outer flow. This is low capillary number, so the free surface doesn't deform very much. And we've got the flow in those droplets. Those droplets are very small. It's very slow, so that's creeping flow conditions. And the recirculation is basically generated by the shear induced at the free surface. So we did, so basically we need to couple the flow inside the droplets to the outer flow. This is really the simplest, I guess, order zero model that we came up with, where the flow inside the droplet results from a balance between viscous stresses and pressure gradients. Okay, that's what this equation is giving us. Subject to a boundary condition that we must have no slip on the substrate and a prescribed shear, tau s here at the free surface. Okay, you can solve that easily. That gives you a parabolic velocity profile, and this is kind of what this parabolic velocity profile. And now you understand why some of the beads appear to be going counterflow, because if your bead is deep enough inside the droplet, basically near the surface, the flow is aligned with the direction of the free stream. And if you go further, deeper, then you've got this counterflow. How do we get this profile? We need to impose mass conservation. And the mass conservation tells you that this is a closed system. If I take a cross-section here, and I integrate the velocity, this integral should give me 0. So that basically constrained our velocity profile in terms of the free surface shear here, which is tau s. And in fact, you can calculate exactly your free surface velocity, which is going to be proportional to the applied shear, the depth, the thickness of your droplets, and inversely proportional to the viscosity. So this already here you can see this inverse proportionality to the viscosity is apparent from this expression. Now we need the outer flow because we need to calculate the shear imposed on this droplet. Okay, so there's a number of things we can do. I mean, if you take any textbook, fluid mechanics textbook, it will give you the shear on a surface exposed to a steady flow, and it's usually expressed as the friction factor, which is given by this expression for small enough Reynolds number, which we do in our case. Okay, so this gives you the wall shear stress if the surface is free of any defect. In our case, of course, we've got our droplet, which disturbs the flow and therefore induces a shear that is going to be different to that formula. So here we, in order to account for this, we used there's a very nice paper by Pozorikidis that tells you the drag force on a sphere or a hemisphere actually that is exposed to a cross flow. And this drag force is expressed as a function of k. K is the velocity gradient and mu is the viscosity. Of course, the product of the two gives us the wall shear stress, the free stream wall shear stress. And there's a constant here. This constant depends on whether you did a whole bunch of simulations where basically you had a very small spherical cap all the way to a full sphere exposed to the free stream. So this constant can take different values depending actually on this angle, which can be thought of as the contact angle. So with this combining this and this, we can actually, if we basically assume that the The drag is due to the viscous shear, and we basically average this viscous shear on the footprint of the droplet. That gives us this expression for the shear experienced by the droplet as a function of, so A is the curvature of this droplet, and RF is the footprint, the radius of the footprint. Very, very small, both in the free stream and even more so in the droplet. So this is we also did doing that in simulations is not very hard. So we did that. So we've got here the flow over one of the small droplets, but here we did so full Navier-Stokes simulation. We used console for this, and the free surface actually could deform, but we see actually that the free surface, given the flow conditions, so the outer flow Reynolds number is 10 to minus 2 here. And you see this recirculation here, high velocity near the top, of course. It's all symmetrical because the Reynolds number is so small. So this all appear to make reasonable sense. And here we've plotted the wall shear stress on the upper wall and the lower wall. And so this is the blue is the lower wall, red is the upper wall, and the dashed black line represents the correlation I was showing you before. So that does a good job. So that's a reasonable job anyway. And here we are plotting the velocity profile across the droplet here. One of them is so the dash curve is the numerical solution, and the red curve is our simple analytical solution. So that's not perfect agreement, but there's a lot of assumption in the simple model that I've just described. So that's for the purpose of what we want to do. We hope that this is enough. So then we did a bit of a parametric study, changed a whole bunch of things like the outer flow Reynolds number, changed it by 2 orders of magnitude. The shape of the hemisphere was changed. The viscosity ratio between the outer and inner flow was changed. And here this is showing the analytical prediction versus the numerical prediction. This is the unit line. So the agreement is not perfect. Sometimes it's slightly above, sometimes it's slightly below, but the calibration curve here has got an exponent of -1. So that should give a proxy for estimating the viscosity. So how does that work in practice? So this is sort of comparing. So for a given viscosity, this is the bit velocity from the analytical solution I've just presented. So that's actually the maximum velocity, the apex velocity, compared to the kind of velocity that was measured. So for some very low viscosity, the agreement's good. The agreement degrades with an error of about 48% for very high viscosity. So that's well, that's obviously not ideal, but we've got to bear in mind that in order to actually estimate this viscosity here experimentally, they've used a correlation. The correlation itself had a lot of uncertainty. So and on top of that, there's a lot of there are many simplifications in our model. 2D versus 3D. The model is plane flow, whereas in reality, of course, we've got a 3D configuration. There's many uncertainty in the experiments, such as the contact angle, which is poorly quantified. So the experimental correlation was based on an average velocity, and of course, because they don't know where the beads are actually traveling, it's impossible to tell whether it's near the surface or near the bottom. So all things considered, I guess this provides a decent estimate of what the viscosity ought to be. And well, not just it provides an estimate, but it also provides insights, so physical insight into the various relationship between the applied shear, the size of the droplets, and and other things. So I guess the takeaway message here is that using this mobility technique is a proxy for finding out the viscosity when the sample is extremely small. I'm going to talk a little bit now about another example where we can't measure the rheology because the sample is very hot. So I'm going to talk about lava. And in fact, this was a project we worked on for a number of years. It was funded by Marsden, which is a New Zealand funding body, involving a lot of people. But I guess I'll mention Ben Kennedy is a volcanologist, and he's always got lots of interesting lava problems to talk about. Jérôme Monnier from INSA Toulouse, and some of the work I'm presenting is mostly the work of those students here, Raman, David, and Dale Cusack. So I'll start with this, actually this nice figure from a paper back in 2015, which inspired a lot of the work I'm talking about here. So this was a laboratory experiment with lava, and they were looking at how the lava was deflected by a wedge. And I really love this picture because there's a lot in it. You can see the temperature field, you can see the free surface velocity field, and the question again was like, well, how can we use all this information to quantify the rheology of the lava? When you look at this table, this is a table taken from classical textbook to do with volcanoes, the Encyclopedia of Volcanoes. And you see that this is measured viscosity here, and using various methods. You see that you got numbers ranging from 10 to the 2 to 10 to the 5 or 10 to the 6. So obviously the viscosity varies by orders of magnitude, and the reason for that is because the viscosity, or the rheology more generally speaking, is a function of the temperature, the chemical composition, and the crystal and bubble content. So there's a lot of variability. I tried asking ChatGPT what is the correct answer, what is the correct rheology for lava, and he came up with those three rheology, which are I guess as far as generalized Newtonian fluid, that covers the whole thing from Newtonian to Bingham plastic to Herschel Berkeley model. So the first thing we try to do, I didn't know at the time that we could actually do lava in the lab, but this is what my volcanologist colleague told me we could do. So we did some simple experiments where we basically put a bit of lava in a V channel, or put it on a substrate and let it spread, and try to see whether the front position can tell us something about the viscosity. Again, so far I'm going to talk about viscosity. So if you want to know how to make lava at home, here's a bit of recipe. So you take some rock, in that case that's obsidian. You grind it really fine. You put it in a bit of a crucible. You heat it up to a very high temperature. In fact, we've added a bit of flux. So flux is a chemical compound that basically lowers the melting temperature, and then we deposit it on a surface and see what happens. We try to excuse me. The melting point. Okay. It can be anything with the flux. Actually, it can be about 800 degrees C. Without flux, probably more like 1200. So yeah, it saves a lot of energy. So then we try to do it on a larger scale, and Dale is on the right-hand side here, was a PhD student I co-supervised, but here the amount of energy we used to produce the kind of lava flow that you see here was too much. So anyway, we stayed small scale. So here what you see is the lava, still very hot. It's going down this V channel, and there's a classical paper, a nice paper by from Uppert's group, that basically say that the front, there's a similarity solution that tells you that the front should advance like t to the half. Okay, so, and all this prefactor here has got a bunch of things. Most of them are geometrical parameters. V is the volume that you pour, and but what you don't know is this nu. Nu is the kinematic viscosity. So you see that if you do an experiment, you plot the position of the front versus t to the half, you get this prefactor, and if you know everything else, you can calculate this kinematic viscosity. So this is what they all did, and you know, square roots of so the front position versus square root of time does give a nice straight line here, and does allow you to estimate the viscosity. So here this is the viscosity as a function of the percent flux in the mixture, and the more flux you have, the lower the viscosity, basically. So that's sort of made sense. We wanted to sort of cross-validate this, and there's another paper from Huppert, a very classical one, that says that if you've got a gravity current, if you put a bit of a lava in that case on the surface, it's going to spread at a certain rate, and for a fixed volume, this basically should spread as t to the 1/8. Okay. Again, if you plot your radius of spread versus t to the 1/8, you can calculate this prefactor, and this prefactor again is related to the kinematic viscosity. Okay, so we did that, and here what you see on this graph is basically the log of the viscosity versus the percent flux measured either on the flat plate, so the gravity current configuration, or the V-channel configuration. Okay, this is log of the viscosity, so the difference between the two may be a little bit greater than what it seems, but at least it seems to be giving a reasonable order of magnitude of what is going on. All right, so following on from this, so far I've only talked about Newtonian fluid. They're very interested, but of all probably the most boring rheology, really. So we wanted to then test what we could do with in a different configuration, and what we tested was the dam break problem. So the dam break problem, it's a classical problem. You've got a gate that separates basically a region of fluid with a high depth to a region of fluid with a lower depth, and you pull the gate, and obviously hydrostatic head drives the fluid from high to low. So if you recall when I talked about inverse problems, so we need two things. We need observations. So how we got the observations that we were interested in is the free surface velocity. And the free surface velocity, we basically seeded the free surface with polystyrene beads, and and those beads were basically tracers that we could use to basically to calculate the free surface velocity using a colleague at the University of Canterbury developed like a PTV, a particle tracking velocimetry software called Stream2. And from that we were able to therefore calculate these are the trajectory of those beads, so Lagrangian trajectories. So this is, and from those Lagrangian trajectories, we can calculate an Eulerian velocity field. And this is, I should say that this region here corresponds to an area which is quite close to the gate. And down here we see the free surface velocity at different times. So this is early time, so we've got large velocity concentrated near the gate, and as time evolves, the velocity decreases and spreads further downstream as the current basically travels downstream. Yep. Yes, it's in the correct. Yeah. Yep. All right, so this constitutes our observation. So we need a model. So we can do two things. I mean, first, of course, we can just try to solve the whole Navier-Stokes, but and it's possible, and we've done it, but it's expensive. And usually, in order to solve those inverse problems, you need to evaluate your objective function many times. So you want to cheaper model to run. So I'm going to, we solved the full Navier-Stokes, but I'm going to talk about a simplified model that we derived. It's quite classical, but when your fluid is described by a power law, so this is our power law here. So we've got the viscosity, which is basically proportional to the strain rate to the power n minus 1, K being the consistency and n being the flow behavior index. We can, these are the two unknowns. These are the things that we would like to recover from the free surface velocity. So we, if you do sort of, in the experiments that we did, we had a rather shallow pool. It was 1 or 2 centimeters, 2 or 3 centimeters deep, basically. And therefore we can, well, we try to use a depth average model, sort of lubrication approximation type model that basically boils down to two partial differential equations. These are coupled, one for H, which is the depth of the fluid layer. And if you look at this PD, it's highly nonlinear, but really it's, well, it's second order for the pressure. And the pressure has got two components. Pressure P has got a hydrostatic component, and we've included the surface tension component, which is this term here that involves the curvature. So this is just two PDEs, and of course this is a lot cheaper to solve than the full Navier-Stokes model. And this model has got our two rheological parameters that we try to recover. Okay, so I'm going to skip through that. We basically solved this in COMSOL, and there's nothing too interesting to say. It just works reasonably well. But what we try to do is minimize this objective function, which is a function of our two unknown, the consistency K and the power law index N. And this objective function is basically the mismatch between the modeled and that's the computed free surface velocity and the modeled free surface velocity. So we integrate the mismatch, and we do it for multiple times, basically. And I will say that from our lubrication approximation type model, obviously the velocity does not appear, but the velocity can be related to the depth H and the pressure P, and this is what we see down here in this expression. Okay. All right. So we first did simple experiments called the twin experiments, where you basically cheat the system, where you say, I'm going to run a simulation with known values of K and N, build my own free surface velocity, and then I'm going to start from a different. So this is my parameter space here. I've got N, I've got K. This is my solution, and I'm going to start from another point and see whether steeper descent type algorithm is going to take me there. So we did that, and when you we generated some fake experiments by picking n equal 0.7, k equal 0.4, and then try to recover those values. And what you see quite clearly in this, this is the map of the objective function as a function of n and k. And you see a very well defined, so this is the log of the objective function. You've got a very well defined minimum, which is encouraging. Basically, that means that your problem is reasonably well solved, and you should be able to recover those rheological properties. So this is even robust to a certain amount of noise. Here there's a lot of noise, and you still have a very well defined minimum that allows you to recover those rheological properties. Okay, and then we tested it with actually, it was a bit of a boring fluid, but because it was just glycerol, which strictly speaking is Newtonian, but the corresponding values of n, the power law exponent is 1, and k, which is nothing but the viscosity, is 1.17 Pascal second to the power n. And when we use this fluid, this is again our objective function as a function of our two unknown parameters, and we can recover the exponents. N equal 1 is well recovered, and k equal 1.13. So that seems to work, and this is kind of comparing experiments, those crosses and lubrication approximation, and the full Navier-Stokes solutions for the optimal parameters, and you see a reasonable agreement. All right, so lastly, I'll talk about how our motivation was lava flows like this. Actually, this is lava flow. This is quite recent. This is 2024 in Iceland. When you look at this lava flow, well, there's no animation, but I can tell you it actually flows quite fast. So the Reynolds number here, you know, all those approximations I've just talked about, which basically neglect inertia, becomes invalid. So what we wanted to do is develop a model that would allow us to still have a depth averaged flow, because they are easier to solve, especially when you want to do parameter identification, or but still capture the very important rheological property of lava, which is that it has got a yield stress. So certain amount of yield needs to be exceeded before it starts to flow. Okay, so this is actually a simulation. That's the work of David Mukiri, really my PhD student, solving. We've got a bit of lava coming out from the top here. Well, sorry, this is a top view. So we've got an injection point here, and the lava is injected. The plane is inclined at an angle, and the lava flows around those objects. The lava basically builds up upstream of those objects. You can think of them as representing those houses, basically. And in fact, what we were very interested to try to do is to say, hey, if at this point on a house, for example, I can measure as a function of time the rate at which the depth increases. It's called a hydrograph. That's the name of such measurement. Is there sufficient information from that to infer the rheological properties? So we tried that, and I'll summarize a little bit the model. I'm going to have to take quite a few shortcuts here because the derivation was a bit painful. But we've got the Navier-Stokes equations. Here we all recognize them. This is our rheological law. This is Herschel-Buckley, where we've got a yield stress, consistency, and a power law index. And the other things are quite standard. Well, this is the standard kinematic boundary condition. And we may have some slip at the bottom, which is represented by this law. In practice, actually, we didn't take that into account. What you'd expect the free surface velocity to look like is what we see on the here at the bottom right. So we'd expect basically this is the ground. Near the ground, we've got high shear. So the stress exceeds the yield stress. So we've got a sheared zone. This is called sometimes the unyielded zone. And then near the free surface, actually the shear rate becomes vanishingly small, and therefore the shear stress becomes too small, and we don't exceed the yield stress, and we've got basically like a plug zone. Okay, and this is the unyielded region. Okay, the boundary between yielded and unyielded region is described by the yield surface, basically. Okay. So one of the challenges was to develop a shallow water approximation of those equations. So, and this is where I'm saying I'm jumping quite a few steps, but I'm just showing you the final results really. This is the full equation. So we've got the mass conservation here. You recognize Q is obviously my flux. We've got here the momentum conservation. It has been depth averaged. and I'll talk about the various terms in a moment, but I'll just say that, so B is describes the topography. Okay. This is what we see. So we've got our coordinate system like that. B describes the topography. H is the depth, is the thickness of the layer, and capital H is the depth related to the reference frame. So in doing this depth averaging, so we've got some terms which are, so for example, this here, Q cross product with Q comes from the integral of the velocity squared, and we've got a correction term here. So basically those two terms comes from this integration, and we've got those terms in black here that comes from the integration of the depth integration of the pressure. This tau b is the friction term at the base, and you see that this tau b depends on all the rheological parameters. S theta is related to the slope of our flow and the slope of the free surface. I will just say that we recover. There was expression for the power law case and the Newtonian case, which we both recover. So that gave us some confidence that this term was correct. And when we did some comparison with experiments, here we've got the fronts. Actually, there's some beautiful experiments by Anse, where they were looking at basically the flow of kaolin suspension. And we see that basically the green curve here is our simulations. The circles are the experiments. So we see some good agreements. When we look at the flow around an occlusion, again, we see some, so this is a cylindrical occlusion. The free surface rise upstream and the free surface decrease downstream. Again, we've got a reasonable agreement. Okay, having validating things, again, the goal is to recover some rheological properties, ideally 3, the consistency, the power law index, and the yield stress. And again, we do that by minimizing. So now we've got a hydrograph. This is what a hydrograph looks like. At a certain point in the flow, we measure the depth as a function of time. So this is what a hydrograph looks like. What we want to do is find the values of K. This is our vector of control, if you like, to minimize the difference between the modeled and the observed hydrographs. So this is what our experiments looks like. I'm kind of running out of time, so I'll go quickly through it. But basically, we injected some fluid here at the top. Fluid is carbopol, which is viscoplastic. Let it spread and basically recorded the hydrograph at point A here. There's a bunch of parameters, and I will just say that we also measure the actual rheology using a rheometer in order to validate. So this is what I've zoomed in a little bit. Well, this is zoomed in on our cylinder here, and you see the advancing front of the cylinder, and this is what the digital image looks like between those two lines, and that allows us to basically record a hydrograph that basically looks like this. Okay, so this is our experimental data, and then we tried to recover them using by optimization, by minimizing the difference between observed and simulated data. And this is okay. This is different initial conditions, different experiments, because we had 2 types of carbopoles, and this is the rheometer values, and this is the inferred values. And for K, the consistency, tau C, the yield stress, and N, the power law index. So the agreement varies a little bit, but all in all, it seemed to be giving some reasonable answers. And here you see the measured hydrographs and the fitted ones from the optimal values. Okay, I'm about to conclude, so I hope I've convinced you through this talk that there is a lot of information that we can recover from free surface. There's still lots of challenges and interesting problems. Generating high quality observations is difficult. Developing good models that can be solved quickly is a challenge. Here I've almost always made some a priori assumption about what rheology to use. That's obviously a limitation. Questions on equifinality and the uniqueness of the recovery is also a difficult one. And then there's more physics. In lava, of course, non-isothermal effects are important, and non-equilibrium chemistry is also important. So there's plenty of problems still to work on. So I'm just finished. I just want to put this last slide for you, because I suppose in the crowd there's a few you who likes fluid mechanics, but in 2026 we're organizing the Australasian Fluid Mechanics Conference. This is in Christchurch, so that's the city where I live, beautiful city, and therefore, yep, this is in December 2026. If you want to escape the grey Paris days and come to beautiful New Zealand, you'll be welcome. Thank you.
Thank you very much, Mathieu, for this very nice talk and many topics on inverse problems. Are there any questions?
Thank you. So we have a question about another material that you didn't talk about. So you said about landslides.
Yeah.
Have you already used the rheological laws coming from granular materials with the friction?
No, I haven't yet, but okay. I want to, because I know there's a lot of an analogy, and well, I know that sometimes granular materials can be described as a Herschel-Berkeley material, but I haven't done that yet. But I'm definitely interested in looking into this. Especially landslide is a very topical problem, especially in New Zealand, actually. Yep.
I have a question on your inverse problem formulations. So usually I've seen people, when they introduce these problems, they also introduce a regularization term.
Oh, yeah.
Do you also do that, or is it necessary?
Yeah. No, none of these problems it was necessary. I think it's because regularization, well, here actually from an inverse problem point of view, it's not very ambitious. In fact, it's probably not considered a true inverse problem. It's only a parameter identification problem, really. And so we're only trying to recover 2 or 3 material properties, and therefore I think it's, well, even though it's not guaranteed to be well conditioned, it's not like we're trying to recover a whole field of data that we don't know, and where really you truly have ill-defined inverse problem. So I think because the problem was reasonably well conditioned, we didn't have to do that. Yep.
Okay, thanks.
Thank you.
Thank you. Maybe I missed something. It's about the droplet problem.
Yep.
Is the gas flow supposed to be uniform across the transverse direction, or is there a boundary layer? And if so, how does the droplet height compare to this layer?
Okay. Well, actually, so yeah, in fact, maybe my figure was a little bit misleading, because I've got a uniform flow at the top, but well, I guess a couple of things. First of all, the friction factor that we used, the correlation, is actually that's actually assuming that it's a boundary layer flow on a flat plate, basically, so your question about the size of the boundary layer relative to the thickness of the droplet, I have not checked, so I couldn't say with 100% certainty, but maybe yeah. Yeah, that is correct, and I guess I was going to pull out this I mean, actually, so this kind of shows the development of the boundary layer. I guess from the point of view of using this correlation, I think it seemed to be reasonably valid, actually, like this graph actually suggests. But yeah.
Hi, thank you for your talk. I had a question about going from a carbopole to a lava.
Mm-hmm.
Have you a strategy to do the same thing in lava, where you have variations of viscosity with temperature, with chemical properties, and so on? And
Yep.
about the simulation that you showed, was it a simulation where you inject lava and it hits some kind of building?
Yeah.
Are we in a regime where the properties of lava are almost uniform, or are they huge, or does it solidify? Or?
Yeah, the simulation that I showed, it's isothermal, so we don't worry about this. I mean, actually, I'm just coming from last week. I was at a workshop on modeling lava flows, and doing the depth averaging of the energy conservation equation is definitely not straightforward, and therefore combining shallow water equation with depth averaged energy equation is already a bit of a challenge. And then after, from coming back, I think, to your earlier point in your question, yeah, if you are trying to identify properties which are now a function of the temperature, of course you multiply your complexity of your problem. But in fact, usually this there are some pretty well, for example, the relationship between viscosity and temperature tends to be described by an Arrhenius law, so potentially this can be parameterized. But then otherwise you can do things, and we started doing a little bit of that, where you try to recover not just parameters but a full field, in which case you can account for things which are spatially dependent, but it definitely gets complicated. Yep.
If there's time for one last question. Thank you for the talk. A side question, a curiosity question. Wouldn't you measure the viscosity of your fancy fluid by just having a droplet sedimenting in a stationary fluid? Because you got the solution, and from the analytical point of view, you got the solution by J. Taylor from the 60s.
Yep.
So
And this is used sometimes, but practically, for the first example I was talking about, this is not possible, because of course the aerosol particle, we don't have enough samples, so we couldn't. Yeah. You're talking about looking at sedimenting of a
single sedimenting droplet in a fluid.
I see. Yeah, I mean, I see if you got a high column of fluids, that's a
just a sedimenting droplet of the size that you want in a sedimenting fluid in a Stokes flow. You can do even at microliter size.
Yeah. It might be, that's an interesting idea, and it's probably possible. Here we didn't have coming back to the earlier problem of the aerosol particle, we had the top view, therefore we didn't have the height as a function of time. But yeah, I mean, in fact, when you start thinking about it, there's so many different ways you could actually, most problems that we always solve require the rheology, so you can always think of them as inverse problem. Yep. Yep. Sorry? Why did we use PTV? Because because we had tracked particles at and I think, I'm not an expert because I'm really not an experimentalist, but I think in order to use, we didn't have in order to use PIV, I think we would have needed a higher concentration of markers. Here we had a pretty sparse, our floating polystyrene beads were sparsely distributed, so I don't think we had enough to do a PIV. But
there is also a technique developed by Frédéric Moissy.
Oh yeah.
Described, I believe, in Experiments of Fluids in 2015, if I'm not mistaken, in which he in addition adds some like printed dots at the bottom.
Oh yeah.
With the same technique.
Yes.
Develop the height of the interface as well.
Yep.
So maybe as this, you could have instantaneously both the free surface velocity and the elevation. I don't know if we need it, but
yeah, I mean, and since those experiments, I've seen a number of other techniques that seem to be progressing very fast in terms of doing free surface measurements or free surface depth measurements. So yeah, that would be good.